And you can bring your trivia sheets and golf pencils up to Sam at the front. Don't forget the golf pencils, please. I'm going to introduce you.
To the slides, but apparently not.
Okay, everybody hopefully got their trivia sheets in. We're gonna get started. So we only have one talk tonight, unfortunately. As you know, we had to cancel Astronomy on Tap at its usual time slot because of the weather. So the other speaker that was here was actually just visiting from California, so she's no longer in Seattle. She's no longer with us. She's still alive though. But that's okay because we told JF that he can just talk for as long as he wants now. And he's going to be talking about dark matter murder mystery. Now, the fun thing about JF is that he's defending his PhD in a month.
Thank you.
Which means he basically has a doctorate at this point. And he's going to be a postdoctoral fellow at Stanford, which means he's ridiculously smart. So with that, please welcome Dr. John Franklin Crenshaw. Tripped on your name.
You know, if Andy hears you already calling me doctor, he might not give it to me.
It's a good thing he's not here.
What's the, there we go.
Yeah, you got it.
Can they hear me on this?
I am going to die on this one of these times.
Do I need to also speak into here? Let's do this. Speaking to both.
Oh.
All right, hi everyone. My name is John Franklin. Thank you for the wonderful introduction. I am a cosmologist at the University of Washington, which means I study the origins and evolution of the universe as a whole, and I use astronomy kind of as a lens in which to do that. And tonight I'm going to tell you about a dark matter murder mystery. So first, I'll explain a little bit about what cosmology is. It's basically, it's kind of like doing archaeology of the universe. It's kind of telling the story of the birth of the universe, its evolution, how we got to where we are today. Here's a little diagram. We started with the Big Bang. You might have heard of it. The universe was really hot, really dense, and expanding really fast. The early universe was filled with a hot plasma, so everything was kind of sloshing around, kind of like the center of a star. It expands, everything cools down. And then all these random fluctuations that exist in the matter universe, they collapse under gravity and form galaxies. And that kind of turns into what we are today, right? A galaxy formed, it formed stars, it formed planets, it formed us. And here we are sitting today. And trying to figure out that history, that billions of years of history, is the goal of cosmology. And we've been doing a really good job of it, actually. So we have a really successful model of the universe that we call lambda CDM. That's what that is, lambda CDM. And that's our kind of standard model of the evolution of the universe. And it's ridiculously successful. With only a few ingredients, it explains the fluctuations we see during the Big Bang. It explains the large-scale structures, so kind of how are all the galaxies kind of spread out across the universe. It explains the process of galaxy formation and how galaxies come together and form big clusters. It explains the features of the intergalactic medium. So you might not know this, but most of the matter in the universe is actually spread out between the galaxies. That's the intergalactic medium. And it explains things, for example, like what do supernovae, exploding stars, look like in distant galaxies? And this is just a few things. I kind of want to give you an idea that it's just a wide different variety, totally different kinds of things are all explained by this simple model, which is really exciting because that tells you it's a really good model. So what is lambda and what is CDM? Well, lambda is the cosmological constant, also known as, more generally known as dark energy. It's this thing that we think is making the universe expansion get faster and faster. The expansion rate is accelerating. We don't know why, but we call the thing that's causing that dark energy And similarly, dark matter is what CDM stands for, cold dark matter. Cold just means it's moving slowly compared to the speed of light. It's not flying around at the speed of light. It's kind of sitting down like regular matter does. And it turns out this pie chart, this tells you the contents of the universe. And it turns out that regular matter, so the stuff that makes up tables and chairs and people and planets and stars, that's only 5% of the contents of the universe. Dark matter makes up another 25%, and 70% is this mysterious dark energy. And so what's cool and weird and exciting about lambda CDM, our cosmological model, is it explains a lot of stuff really, really well, but it kind of rests on these two big pillars, dark matter and dark energy, that we don't really know what they are. And so that's cool because we can do a lot with our model, but it also gives us a lot of really interesting questions to answer, right? Basically the big goal of cosmology right now is to figure out what are these two things. And so this gets to a question I often encounter when I talk to people about my science, just kind of out in the public. Aren't dark matter and dark energy just fudge factors? Isn't this just a sign that your theories don't actually work? And so my goal today is to explain to you what is dark matter, why do we think it's real, why saying it's just a fudge factor doesn't really even make sense, and we're going to do this using an analogy to a murder mystery. That's Hercule Poirot, if you don't know who that is, Agatha Christie fame. So we'll start by just talking about, okay, like what do I even mean when I say dark matter, right? So dark matter is this hypothesis that 80% of the matter in the universe, and you're probably confused, I should have clarified this. Before I said it was 25%, it's 80% of the matter, and then the rest is all this dark energy, right? So 80% of the matter in the universe is invisible to us. And really, we should call it transparent matter, not dark matter. It's not dark. Like if you looked at it on the universe, it doesn't look like a dark cloud. You just see right through it. You can't tell it's there at all. And importantly, it's categorically different than regular matter. You might think, oh, is this just like normal matter that's like not emitting light? You know, like your house is still full of stuff at night when you turn off the lights and the sun's gone, right? Like normal matter can be dark too, but that's not what this is, right? It's categorically different. And even though we can't see it, we can detect its presence by the gravitational pull it exerts on everything else in the universe. And I'll say that over here, well, it's kind of washed out on this projector, but you might be able to tell there's like all these webs. We think the universe is full of this kind of cosmic web of dark matter. Kind of looks like Swiss cheese. So why do we think this, right? This goes back to the 1970s. This is when like astronomers first became convinced that dark matter was an idea worth taking seriously. And what they did was they looked at galaxies. So this is an image of a galaxy right here. And they said, okay, as the function of distance from the center of that galaxy, how fast are the stars orbiting? So galaxies are these big collections of stars. We're talking about specifically disk galaxies. So they line this disk, and the stars orbit the center of the galaxy. And you just want to look, okay, as a function of distance from the center, how fast are they orbiting? And this is interesting because, as you might know, if you played on the merry-go-round at the playground as a kid, when you're on something that's spinning like this, it kind of wants to throw you off, right? And the faster it spins, the harder you have to hold on so that you don't fly off the merry-go-round. And it's the same way with stars in a galaxy. The faster they're orbiting, the more force you have to apply to keep them in the galaxy so they don't just fly out of the galaxy. And so, what's the force pulling on them? It's gravity from all the mass, all the matter that's in the galaxy. And so by looking at these curves of, what's the orbital rate as a function of distance, that tells you about like what's the distribution of stuff in the galaxy. And so what these astronomers expected is that as you go outwards, you're kind of, you're moving outwards, so there's more stuff between you and the center of the galaxy. And so they're orbiting faster, right? Because they have a stronger pull on them. But at some point, you get to this point where now you've kind of passed all the stars. And so as you get farther away, you don't really add a whole lot of extra stuff. You're just getting farther and farther away. And gravity gets weaker the farther and farther away that you are. And so the orbital velocity would have to fall off. That's not what they observed. Instead, they observed this curve, right? It rises, then it kind of plateaus, even continues to rise a little bit. And what was weird about that is all these stars, they're way above this curve, right? What that means is those stars are orbiting way too fast. From what you can see, this galaxy does not have enough mass to exert enough gravitational force to hold these stars in. So all these stars should just fly out in the universe. They should all just fly out on their own, and the galaxy should disappear, right? It should be disrupted. It should not be able to maintain its kind of cohesive structure. And this was a big hint something weird was going on, because they observed this in a bunch of galaxies. And this was a hint that there's more stuff in there. There's more stuff doing the pulling, right? Something must be holding onto these stars. A lot of these observations were pioneered by this very famous astronomer named Vera Rubin. I actually work on the Vera Rubin Observatory, this big, beautiful billion-dollar telescope in the Chilean Andes. And it's named after her because one of the goals of this telescope is to unveil a lot of the secrets of dark matter. I'll get to that later on, but I wanted to give a shout out to Vera Rubin because she's a really awesome astronomer. But she was not the first person to find evidence for dark matter. Well, he is really washed out over there, but that is Fritz Zwicky. He was a very famous astronomer in the early 1900s, and in the 1930s, he observed what's called the Coma cluster. So this is a big cluster of galaxies. If you look at this image, most of the points that you see are very distant galaxies in the universe. But you see there's a whole lot of these kind of like fuzzy white blobs. These are all giant elliptical galaxies that all live together in this cluster. So they kind of all live in the same neighborhood together. And just like how in a galaxy, all the stars are kind of swirling around, in a cluster, all the galaxies are swirling around. And so Fritz Zwicky did a very similar thing. He said, okay, these galaxies are in a cluster. Let me look at how fast they're all swirling around each other. And from that, I can infer how much mass is required to hold them in. And he found the exact same thing, right? These galaxies are swirling around too fast. This cluster does not have enough mass. They should just fly out into the universe. The cluster shouldn't exist. So how does this exist? And again, it's this repeated pattern. There's more stuff doing the pulling than we can see with our telescopes. So the first thing you might think, right, is kind of like I said earlier, we don't need some exotic dark matter, right? Like maybe it's just more regular matter that's not emitting any light. So maybe it's just dust, just dark gas. It's a lot of mass, but it's not emitting light. We can't see it, right? It turns out this does not work. So the Big Bang theory, the theory of the early universe, where it's really hot and dense, it's so hot and dense that the whole universe is like a nuclear reactor. And so hydrogen is fusing to form helium. Hydrogen and helium are fusing to form lithium. They form beryllium, et cetera, up the periodic table. Now, if you know the laws of particle physics, as us physicists like to think we do, you can look at the Big Bang, and you can say, I can predict how much helium should be created during the Big Bang. I can predict how much lithium should be created during the Big Bang. All you need to know is how much regular matter is there in the universe. If you tell me that, I can tell you the abundance of these elements. And that's what this plot on the right here shows. The x-axis is the density of ordinary matter, and the y-axis is the relative abundance of these different elements compared to hydrogen. So what this says is that, for example, at this point here, for every atom of hydrogen for every 10 atoms of hydrogen we have one atom of helium. We have a lot less deuterium, which is like a heavier version of hydrogen. We have a little bit less helium-3. And then way less than that, we have a little bit of lithium and not a whole lot else. But the important thing is that we can predict, as a function of how much matter there is, we can predict how much these elements there should be. And so astronomers, they're very smart. They go out, they look, they do an inventory of the elements that we can see in the universe. And they see that very clearly we have this much helium, this much deuterium, and this much lithium. And they all line up on this line. It's great. And this tells you how much regular matter we have in the universe. And so remember, I told you that 80% of the matter is this dark matter, right? So that means there's 4 or 5 times as much dark matter as there is regular matter. And if you were to say, okay, well, let's just imagine all that's just regular stuff, it's just dark, that does not work, because that would totally screw this up. You would not end up with the right amount of helium in the universe. You would not end up with the right amount of lithium. And so this evidence tells us this dark matter, it has to be categorically different. It's its own kind of thing. Another big thing that came later is we found convincing evidence that it's not just that like this stuff is exerting more gravity, it's that it's located at places where the regular matter isn't even located. So what you see here is what's called the coma cluster. Sorry, not the coma cluster, the bullet cluster. And what actually happened is two clusters, they were falling towards each other, getting pulled by gravity, and they hit each other and passed through. And so I'm gonna pull the microphone away for a second, going like this, and they're just gonna swirl back and forth and kind of slowly merge. And what we're seeing is just after their first collision. And what all this red stuff in the middle is, that's all the regular matter, all the hot gas that emits X-rays. We can see it in our telescopes. As these things collide, all the gas, it hits each other, so it kind of stops, right? If like you and me ran into each other, we don't pass through each other. We kind of hit each other, we stop, everything gets messed up. All the blue, we can tell this is where most of the mass of these clusters are, because that mass distorts the light of the galaxies behind it. Because that mass warps space-time, and that warps the paths of the light that comes to us. And so by looking at the warping of the light behind these regions, we can tell that this is where all the mass is. So what we have here is we have these two clusters that have collided. We can see all the regular stuff, as you would expect, right? It collides, it kind of stops in the middle. But most of the mass just kept going. It didn't care. They passed each other like ships in the night. And so this is evidence, right, that all this extra matter is not even located where the regular matter is. And so you can't just say it's the regular matter and the gravity is different. And it's the same story with the CMB. So this is what's called the CMB. It's the light that's left over from the Big Bang. So if the Big Bang is this like really hot fire, what the CMB is it's like the leftover embers that are glowing after the fire. And we look out in the universe and we can see this light, and this is our great evidence that the Big Bang actually happened, because we can see all that light from the Big Bang. And these cosmic embers, they have all these tiny fluctuations in them. And our theory of cosmology actually predicts what all these fluctuations should be. But importantly, we can't predict what they look like unless you assume there's dark matter. And I won't go into the details of it because it's fairly technical. It would take a whole talk all by itself. But we can't explain these patterns unless we have the dark matter. And this is even more important because these fluctuations collapse under gravity over time. They start really smooth, and they form all the structure we see today. And so when you look at this, kind of the red spots are kind of over-dense areas, and the blue spots are under-dense areas. So the red spots are going to collapse and form galaxies and clusters and stuff like that, right? So the Earth, you and me, our kind of cosmic origins lie in one of these overdensities. The problem is there hasn't been enough time in the universe to form galaxies. The universe is 14 billion years old. That sounds like a long time, but it turns out that if you start the initial conditions of the universe, if you apply the cosmological models, our understanding of physics, we find out is we don't have enough time to form all the galaxies we see today. Not to mention the fact that we see that galaxies, we might have heard of the JWST space telescope, sees that galaxies form really early in the universe. And that shouldn't be possible. There's not enough time. Dark matter is the solution to that as well. It gives a boost in the early universe because all the regular matter, it's sloshing around in this primordial plasma, that kind of hot fusion state in the beginning. But the dark matter, it doesn't care, right? It doesn't interact. It says, whatever. I'm going to collapse. I'm going to form structure. And so while the Big Bang is happening, the dark matter is already forming structure. So that when the Big Bang ends, all the regular matter can say, okay, well now I'm going to fall in to all these wells created by the dark matter. And that gives a big boost to galaxy formation. And so the fact that galaxies exist, the fact that we even exist, is evidence that this dark matter exists, right? We need something to cause galaxy formation to occur, because otherwise it wouldn't have happened. And so today, every galaxy that we know of lives inside a big cloud of dark matter. So there's a dark matter halo, a big bubble of dark matter, and sitting in the center is a little galaxy. And we're just like that. Okay, so back to our mystery. Someone has been murdered, and in this analogy, that's that dark matter exists, right? And what's our evidence? So we have that galaxies rotate too fast, galaxies swirl around in clusters too fast. The abundance of helium and lithium are just right to match this dark matter hypothesis. There's extra gravity even where the regular matter isn't sitting. The fluctuations in the CMB, this leftover light from the Big Bang, requires dark matter to explain it. Galaxies form very early in history in the universe, and that allows our galaxy to form, and we exist, right? These are all pieces of evidence in this puzzle. But we don't know what the dark matter is. What is the thing that's doing this? And so you imagine, we're at an Agatha Christie dinner party. Someone's been murdered. We can clearly see the crime. I explained to you all the ways we can see this crime, lots of evidence. We don't know who did it. And that's the situation that we're in with dark matter. And so we go back to this question, right? Is this just a fudge factor? It's like, what does that even mean? Like, someone has been murdered, right? Just because we don't know who the murderer is doesn't mean that the murderer is a fudge factor, right? If I don't know who did the murder, and you're like, oh, it's a fudge factor, then I'm like, okay, well then, like, how did the knife get in that person's bag? Like, can you explain it to me? Please. Like, what does it even mean to say it's just a fudge factor, right? We have all these mysteries, we have to explain them. So we need to crack the case. And what's the first thing you do when you crack the case? You ask yourself, who are the suspects? The first suspect up are called WIMPs, which means weakly interacting massive particles. And that's just a kind of funny acronym to mean they're heavy, they're massive, and they're weakly interacting. They don't interact very much. In fact, technically, they interact via the weak nuclear force, which you might have heard of if you know any particle physics. But basically, it means what it says on the tin, right? Interacts very weakly. WIMPs were super, super popular. In fact, they're predicted by supersymmetry, which is a super popular theory in particle physics. Particle physicists thought for a long time that WIMPs should exist. There should be tons of them. The astronomers came along and said, oh, we need a whole bunch of extra matter. They're like, oh, we have a great candidate for you. And it turns out if you applied the kind of standard theories of WIMPs to the universe, you'd predict the exact right, perfectly the right amount of dark matter that we see in the universe. And this is called the WIMP miracle. You're like, oh, this is perfect. WIMPs have to do it, right? And so we've spent decades now, about 4 decades, building experiments that are getting more and more precise, more sensitive. And your detector is sitting around waiting for a dark matter particle to bump into it, right? Because galaxies form in these dark matter halos. We live in a big cloud of dark matter. So we think there's probably a lot of dark matter swirling all around us right now. And they interact really weakly, not very often. But if they're WIMPs, they should interact sometimes. So let's just build some detectors and wait for dark matter to bump into our detector. And this is what it looks like, right? Dark matter comes in, it hits something in your detector. You have an interaction, and that creates electrons in your detector. And we know how to detect electrons, right? And we can say, OK, I think this was a WIMP. This is an image of one of the best WIMP detectors in the world, or would-be WIMP detectors. They've not detected any WIMPs. It's called xenon, although now it's xenon 1T because it's 1 ton of xenon. Xenon is a very inert gas, so it's one of the noble gases, if you remember from your chemistry classes. So it likes to sit around and not do anything, which is perfect, right? Because you want it to sit around, don't do anything unless you get hit by dark matter, right? It's underneath the mountains in Italy, the mountain called Gran Sasso. It's like a mile underground because it turns out that the atmosphere is actually constantly bombarded from particles from space called cosmic rays, and that they shower down the atmosphere all the time. It's happening all around us, and that causes a lot of noise in your detector. In dark matter detectors, you're looking for something really rare interaction. And so if you have all these constant cosmic rays, you're never going to see it, right? You'll be looking for the needle in the haystack. So you want to get rid of the haystack so you can see the needle. And so you build these things deep, deep underground. Another thing, get rid of more of the hay to find the needle, right? Is that you want really low radiation materials to build your detectors. And it turns out all metal in the world is somewhat radioactive. that radioactivity decays over time. It's kind of what the half-life is about, right? So if you forge new metal, it's going to have some radioactive elements in it. If you wait a long time, that radioactivity disappears, and then that's going to stop making noise in your detector. Okay, so let's build our detector out of really old metal. But we have a problem. In the 20th century, you may know that a lot of governments started blowing up nuclear weapons. Well, not a lot, us and Russia. Not just in World War II, but in nuclear testing and the Cold War. And every time you blow up nuclear weapons, it litters radioactivity across the entire globe. And so that raises the radioactivity of any metal that exists that it can find, right? And so ideally, we want metal that's really old, but if it's old, it's before the Cold War, and so it's going to have this problem. So we want old metal that was protected from this radiation from these nuclear bombs. Well, it turns out that water is a really good shield for radiation. That's why a lot of nuclear reactors, you might have seen them glowing underwater, like in nuclear power plants. And so what's a good place to find really old metal underwater? Roman shipwrecks in the Mediterranean. And so they've literally excavated metal from these Roman shipwrecks and used that to build these particle detectors. Now my sister, I'm a physicist, a cosmologist. My sister is a classicist. She studied classics in graduate school, like Roman culture, all that kind of stuff. And so I asked her, I was like, does it make you mad that we melt down these Roman artifacts to build particle detectors? And she told me, no, that we have so many Roman coins that we don't know what to do with them. Please, melt them down. I was like, okay. Okay, so the particle physicists had this WIMP miracle 40 years ago, building all these detectors, trying to figure out, is it WIMPs, right? And it's not like it's a single WIMP and you can go find it and say, yes, it's this guy or not. It's not a true murder mystery, right? There's a whole different kinds of WIMPs you could have. So this plot, the x-axis is the WIMP mass. So the left side is really light WIMPs, really light comparatively. They're still heavy, right? Because they're massive particles. The right side is really heavy. And then on this y-axis, it's how strong is their interaction rate. So stuff up high interacts a lot, and stuff down low interacts rarely. And so when you build a new experiment, for example, this one, DOMIC here, this is an experiment at the University of Washington. What you do is you build an experiment, and it kind of carves out this space. And so DOMIC said the WIMPs could not be anywhere above this line, right? If it had a mass of 10 GeV and it was more reactive than this, then we would have found it, and we didn't. And so you carve out some of this space and say that space is excluded. And so you build better and better experiments to carve further and further down into this space, to carve away that parameter space. And so you can see, well, I should tell you, this dashed line here is called the neutrino floor. And that's kind of a limit where if the true dark matter particles live down here, it's going to be really hard for us to find them. They're going to have to think of new ideas. So for a while, this has been, for a while, the idea has been that this is the best we can do. Let's try to get there. And you can see we're getting really close, right? We've carved out most of this space. There's only a little bit of gap left where the WIMPs could live. So maybe the WIMP lives in there. Maybe it's under this neutrino floor, and we're going to have to think bigger, better ideas to find it. But the point is, we spent 40 years. We haven't found WIMPs yet. The most obvious values we thought it would have, turns out those weren't right. And so WIMPs are not, off the hook. We don't know it's not them, but they're not quite such a juicy target as we thought they were. So that's led physicists to think, okay, what could other ideas be? That leads us to the axion. The axion is my favorite dark matter particle. It was originally hypothesized to solve this big mystery in particle physics called the strong CP problem. Don't worry about it. It was called an axion after this detergent brand because it cleans up this problem in particle physics. That's not a joke. They literally did that. Unlike WIMPs, axions are really, really light. So it's like the opposite end of the spectrum. And you might know, if you know anything about quantum mechanics, is that all particles are actually waves. And the lighter a particle is, the longer the wavelength is. So a WIMP is really heavy. It's a really short wave, so it's basically a particle, right? We can't really see its waviness. But because axions are really, really light, they actually have long wavelengths. And so the waviness of this particle really matters. And it's quickly becoming a chief suspect. Because, as you can probably tell, it's nice when your problem and someone else's problem can be solved by the same hypothesis, right? Kind of gives you more circumstantial evidence in your case to build. And the reason that I love axions is because the University of Washington is like the world center of axions. We're like the experts in that stuff. And the best axion experiment in the world is ADMX, the Axion Dark Matter Experiment, and it's on campus. This is a picture of it. It's a lot bigger than it looks in this picture. It's a giant super magnet. It's a really strong magnet. They super cool and put underground. And it's asking the question, what if dark matter does interact with light, but only in the presence of a really strong magnetic field? And so that's kind of a natural feature of axions, if it is an axion. And so this experiment is the world leader in kind of searching for this axion dark matter. And this is a bunch of the folks at UW that work on this. Another cool thing about axions is there's something called black hole superradiance. Basically, if axions have a certain range of masses, then black holes should act as dark matter farms, should kind of create and gather these big clouds of dark matter around the black hole. And so you have a black hole and you have a big cloud of axions. And that's really cool because it turns out that black holes are big, the cloud is big, but the distance scales and the strength of gravity scales, it's exactly analogous to a hydrogen atom. So it's kind of like a giant hydrogen atom out in outer space, except instead of a proton, an electron, and electromagnetism, it's a black hole, it's an axion cloud, and it's gravity. And so Masha Bar-Yakhtar, she's one of my friends, she's a professor at UW, she's a world expert in this, and works on, can we find this signal in gravitational wave experiments when black holes kind of collide? Because this axion cloud would play a big role in that process. And so this is a similar plot. The x-axis here is the mass of the axion, with light axions on the left, heavy axions on the right. Remember, this is relative. This is way lighter than the WIMPs were. The y-axis is the strength of the interaction. And you can see there's a huge number of different kind of chunks taken out of this plot. These are different experiments, different astronomical observations. They're carving out different regions of this parameter space. This gold diagonal line is kind of like the favorite region to search for theorists. If the axion actually lived in that line, had a mass and interaction strength that lied in that region, theorists would have a heyday. Like, perfect, this is just what I ordered. And you see, this is ADMX. ADMX is the experiment that really pierces down in there and starts to grab some of that parameter space. And so what they're doing over the years with ADMX is they search the little bar they can, and then they bring the magnet up and they retune the experiment and put it back down, and that allows you to scoot over a little bit and search out a little bit more of that. And they're doing this and carving out more and more of this space. And you can see that the excitement about axions is younger than the WIMPs, and there's a lot more of this kind of viable parameter space left over for the axions than there are for WIMPs. And so we still have a ways to go. Okay, so we talked about WIMPs, and we talked about axions. These are different particles that theorists really like. You could ask, okay, what if it's not like a small particle? What if it's a big, huge thing? And that's what MACHOS stands for, a massive compact halo object. And so, for example, a type of MACHO might be a primordial black hole. So these are theorized to be black holes that are formed during the Big Bang. They're really small compared to what we think of as black holes today. They might be the size of like an asteroid, for example, instead of the size of like, a huge star. And you might have a ton of these things kind of flying around. And what's kind of interesting about primordial black holes is it turns out the dark matter is regular stuff after all. It's just all locked up inside a black hole. So it doesn't behave at all like a regular stuff does. And so one of the ways that we search for this, a lot of the trivia questions were about exoplanets and microlensing. That was for the person who's not here. I'm not exoplanets. But I am going to talk about microlensing. One of the ways you look for these is you watch all the stars in the night sky, and you wait for one of these black holes to pass in front of one of these stars. And when it passes in front, that star will get really bright because the black hole acts as a lens. It magnifies. It's like a magnifying glass. The star gets really bright and then dims away as the black hole passes away. We've been watching the night sky for a long time. We don't see enough microlensing events. So that puts a lot of strong constraints on this. We don't have enough of this stuff. These guys couldn't be all the dark matter by themselves, because if they were, we would see a lot more of these lensing events. But maybe dark matter is more complicated. Maybe it's 25% WIMPs and like 75% primordial black holes, something like that, right? So we have other experiments that are kind of searching deeper into this parameter space. This is a proposed experiment, LISA, a European experiment, to put a giant triangle of space lasers up in outer space and to measure the distances of these laser arms and use that to find really long wavelength gravitational waves that could be coming from these primordial black holes kind of swirling around and merging in the early universe. A very similar thing is in these pulsar timing arrays. Pulsars are neutron stars that spin really, really fast. They're kind of like lighthouses out in the universe, and they spin really fast and really regularly. So, one of these guys might flash at us like 1,000,000 times a second. And so these pulsar timing arrays watch all of these pulsars, watch them blink, and try to detect, does the blinking rate change at all? Because if it changes, that tells you a gravitational wave passed between you and that pulsar. And so that kind of constrains, again, kind of all these black holes swirling around and merging. This one's really washed out. But here it's the mass, again, the mass of the black hole, the fraction of the dark matter they could accommodate. And over here, there's a cut. There's a whole bunch of different experiments up here. One comes on here. So again, could it be all the dark matter? There's only a small range of masses that are left for these black holes to be all the dark matter. But there's a lot of it left. It could be, 1/1,000,000th of the dark matter, which is probably less exciting for you to think about. But physicists love to, really put constraints on things. So. Okay, so to recap, we have all this evidence that this murder has occurred. And we have a long list of suspects. We have WIMPs, axions, primordial black holes. I didn't even tell you about interacting dark matter or fuzzy dark matter, warm dark matter, because despite what Megan said, I'm not going to speak forever. So the particle physicists, right, are going down the list of suspects, checking alibi, means, motive. What are the astronomers doing? We're still searching the scene of the crime. And so that's where the Rubin Observatory comes back in. One of its main goals is to really unveil a lot of the secrets of dark matter. And we want to gather more clues out from the universe to narrow down the list of suspects so that the particle physicists don't waste time going down dead ends, right? Now, this method, it's not going to identify a culprit, but it's still extremely helpful because it provides information that's kind of analogous to stuff like, oh, the murderer is a man over 5'10", right? That doesn't tell you who did it, but that allows you to immediately eliminate a lot of suspects so that particle physicists can do a much better job of kind of really finding this particle. And so one really cool way that you can do this, especially with the Rubin Observatory, is with stellar streams. So the Milky Way is not living by itself. We're actually surrounded by a whole bunch of dwarf galaxies. So these are small galaxies that orbit the Milky Way. And they don't just orbit us, we gobble them up. They fall into the Milky Way, we eat them up, we turn them into our own constituents. And what happens as these dwarf galaxies fall into the Milky Way is they get spaghettified, which you might have heard, if you've read about like black holes in pop science, how if you fell into a black hole, you'd get spaghettified. It would kind of stretch you out. That happens to these dwarf galaxies. So a little kind of globular dwarf galaxy falls in, and it gets strung out into these streams. And so this big red stream here, that's a former dwarf galaxy that got eaten up by our galaxy. And if you have a really nice telescope, you can see that there's this long ribbon across the sky that's kind of the remains of this galaxy. And we're actually surrounded by a whole bunch of these ribbons that are kind of whirling all around us, kind of like rhythmic dancing in the Olympics or something. And these actually give us a really interesting way to study dark matter. Because cosmologists, we work on very large scales. We know a lot about how dark matter works on like the biggest scales, right? How does it spread across the universe? How does it form galaxies and galaxy clusters? But our data hasn't told us very much yet about like what happens inside the galaxy, right? Does our galaxy live in just side of like a kind of a big blob of dark matter? Or does the dark matter have internal structure, right? Like maybe there's kind of a hazy blob, but then there's smaller blobs that are kind of moving around inside of us. And in fact, you might expect this because each of these dwarf galaxies had their own smaller blobs, right? They're smaller galaxies that formed in smaller bubbles of dark matter. And when we eat those galaxies, all that dark matter should be retained and should kind of be swirling around inside of us. And so this is kind of the new frontier of dark matter from a cosmological perspective, is trying to understand how does it behave on small scales, like inside the galaxy. And so again, we have some world experts on this at UW. These are three of my friends who are leading these kinds of studies. And up here, well, again, it's a little washed out, might be hard to see, but up here is a stellar stream of a galaxy that has been eaten up, gobbled up by the Milky Way. And maybe you can see that there's a gap right there where like the blue highlighting disappears. And there's another gap, I think it's right there. Oh yeah, it's, it's kind of highlighted in white, I didn't notice that. This kind of white band here shows you where that gap is, and there's a bigger gap over here. And this is a regular stream. I should say this kind of kink and core, it's kind of the interior, the core of that dwarf galaxy. And then this stuff, you can kind of think of it like its spiral arms getting kind of stretched out as it gets beatified. That's what those are. And a regular stream wouldn't have those gaps. But this perturbed stream that you simulated, you said, okay, let's take a stream that looks like this, and let's shoot some dark matter blobs at it. And what that does is it punches holes in the stream. And so we think we can explain the presence of those gaps by hypothesizing that these dark matter halos kind of punch through the stream. Now, this is very hard because the galaxy is very complicated. You know, maybe it's just like a cluster of stars that went through and did that, right? So you have to gather a lot of data. You have to be really careful with your analyses to really confirm that, no, like, we don't think this happened because of regular matter. And that's what these guys are really leading the efforts on. And so we're going to find tons of these streams with Rubin. It's crazy how many we're going to find. And they're going to really be able to constrain the kind of small scale dynamics of dark matter and start to answer questions that can kind of give the physicists clues as to what roads should they really be focusing down to figure out what is the dark matter. Okay, so the last option, right? Are we really sure they've been murdered? If you watch murder mysteries, read murder mysteries, you know they love big unexpected twists. And so maybe they're not actually dead. Maybe they're faking it, Romeo and Juliet style. Maybe it's a body swap. Does anybody know what movie this is? Anyone? Oh, this is the Clue movie. It's so good. Go watch it. But anyway, so, you could ask this, right? And, are we sure, I gave you all this evidence, right? But are we sure that that has to be explained by dark matter? Is there another way to explain it? And, you might be happy to know that people do work on this. There are physicists who spend a lot of time thinking about, are there alternative ways to explain this data that's not dark matter? And by far the most successful, the most popular alternative dark matter is modifying gravity, right? So let's not add extra particles. Let's just change the laws of gravity that regular matter exerts and see, can we explain things? And it turns out MOND does a very good job of predicting galaxy rotation curves. Can't really see anything on this plot, but there's a whole bunch of data through here, and this curve is fit by MOND. And so if you modify gravity in this exact way, it turns out you can actually do a really good job of explaining these rotation curves. And remember, if you don't remember, the rotation curve is just the fact these stars orbit way too fast in these galaxies. They should fly out. The galaxy shouldn't hold on to them. MOND is a different version of gravity where the gravity is strong enough, it turns out, to hold on to these stars. So maybe MOND is correct, right? Well, it turns out that MOND, it answers that, but it struggles with the fact that galaxies swirl around too fast in the cluster. It can't explain why there's gravity where matter isn't. So you can't just say, I'm going to change the way that regular matter exerts gravity, because I need to add gravity where there is no matter. There is no regular matter. And then, most importantly, it really struggles to explain the fluctuations in the CMB. And this is a problem because we started off, we were first convinced by these rotation curves. And that's the most common way it's explained to the public because it's like the easiest one to explain. And remember, I didn't even go into the details of the CMB stuff because it would take a whole lecture. It's complicated. But this is actually by far the best evidence that we have the dark matter exists. This is the one we care about these days. And so to say that, oh, well, Mond can explain rotation curves, that'd be like saying, like, oh, I have a theory the sun doesn't exist because geothermal vents on the ocean floor could heat the Earth enough that we don't need the sun. And you say, like, okay, well, what's the big ball of plasma in the sky every day? Like you wouldn't believe that for a second, right? And this is the problem with Mond, is that it's really focused on explaining a piece of evidence that like okay, who cares, you know? And so it's not uncommon, like on the web, if you read science, pop sci stuff, that they like to cover alternatives to dark matter because it's it's a cool thing to think about. But if the article starts talking about galaxy rotation curves, you can stop reading the article. I mean, keep reading it if it's interesting to you, but don't take it seriously unless they explain the CMB. Because that article is hypothesizing the sun doesn't exist because geothermal vents are on the ocean floor. It's like, okay, sure, whatever. So in summary, someone has been murdered. There's tons of evidence. Astronomers are searching the scene of the crime. Particle physicists are checking the suspect list. And we don't know how long it's going to take to catch the killer. But that does not mean the murder is a fudge factor. Because like something has to explain this, right? And so far, nothing can explain it other than dark matter. So most of us are spending our time figuring out what is the dark matter. But if anyone can come up with a theory that can explain all this stuff that doesn't require dark matter, we would readily listen. It's just right now, dark matter is the only game in town. And a lot of really smart people have been at this for like 40 or 50 years. So it probably is dark matter. And hopefully, we'll find out what it is soon. The weird thing about dark matter, and this is one of the reasons I did not go into direct detection, like the particle physics stuff, is that they, like ADMX at UW, they can discover what dark matter is this week. They would get instant tickets to Stockholm to collect their Nobel Prize. But it's also possible that no one discovers what dark matter is for like 200 years. Because it's kind of this game of just kind of chiseling away until we find it, right? And who knows where it's hiding. So I hope I live to see it. I hope we all live to see it. That'd be really, really cool. But this is a really big, epic murder mystery that's going to be really hard to crack. Thanks. Any questions? Yeah.
So dark matter structure for regular matter expand into the dark matter structure and sort of form its webs because of dark matter webs?
Yeah, so the question was exactly like how did that happen in the early universe where the dark matter formed structure first and then the regular matter? And what happened is the regular matter is getting sloshed around by all the hot plasma because it interacts with the light, and that plasma is like hot photons. It's pushing on all the protons and electrons. The dark matter doesn't care, so it collapses and forms structures, which we think of as wells. They're kind of like holes for the regular matter to fall down. Once the Big Bang ends, all of that hot plasma, it disappears. It turns into the regular matter, and then all the regular matter can fall down into these holes. And so all the structures, like all the cosmic web that was formed by the dark matter, is now inherited by the regular matter. And so all this stuff that we see in the regular matter is kind of living inside this scaffolding that was created by the dark matter. Yep.
Is there any sort of compensation that needs to be done when you do like deep space trajectory analysis for dark matter? Like, does it have an effect at like human mass scale? Yes.
So I believe that what you're asking is, does the pull of dark matter like change like trajectories of like the stuff in the solar system and rockets and stuff like that, right? The answer is no. Because even though there's a lot more dark matter than regular matter, it's spread out all across really big scales. And so on the scales of like the Earth and stuff in the solar system, the sun and the Earth and Jupiter are like far more important. Yeah.
You mentioned with glimpse that going below the neutrino line, is there like a theoretical reason why that would be improbable, or is that just like, hey, it's hard to build?
So the question is, when you're detecting the WIMPs, there's this neutrino floor that's really hard to get under. So I can flip back to it fast enough. Axions. Yeah, so there's this floor under which it'd be hard to find the dark matter. And the question was, is there a theoretical reason to think it wouldn't be under there? Or is that just hard to search for? It's definitely hard to search for because there's a lot of neutrinos. That's a different particle in the universe. It's unlike the cosmic rays. You can't hide from neutrinos by going underground. And so this is kind of a noise level that you can't get around. I don't exactly know the answer to your question, but I know that a lot of the most promising candidates for like actual values of mass interaction strength that were expected by theorists have been ruled out. So I know at least some of those theories are above the floor. I just don't know if there's many below the floor. I should also say that another reason that WEMPs are losing favor is that supersymmetry, the idea that predicted that there would be a lot of WEMPs that the particle theorists loved. That idea itself is kind of falling out of favor slowly because it's a really nice idea. But there's the big particle collider in CERN in Geneva, Switzerland. And if supersymmetry were real, they thought they would have found a lot more particles already at that detector. And so the fact that they haven't found all those particles makes them think that maybe supersymmetry is not real, which makes them think that maybe the WEMPs aren't real. So, you know, the WEMPs, their alibi is starting to check out. Yeah. Mm-hmm. Yeah, so the first question is, you know, should we be concerned that you go underneath the Earth to go find the dark matter if the dark matter doesn't care a whole lot about the regular matter, right? Why would it be underneath the Earth? And the idea is that the dark matter is everywhere. It's kind of, it doesn't interact, right? So it floats through the table, it floats through your body, it floats underneath the ground because it doesn't hit the regular stuff. It just kind of keeps going. It's like a ghost. And so, you know, you could detect the dark matter on top of the Earth because it's here too. It's just that all the other stuff, all the nonsense, like the cosmic rays, are also on top of the Earth. So you don't go under the Earth because that's where the dark matter is. You go under the Earth because that's where all the other stuff isn't. And it blocks out the stuff, all the noise coming from outer space. The second question is, how are dark energy and dark matter related? And is it like a Luke Skywalker, Darth Vader kind of situation? They're related in the sense that they both have the name dark. And in both cases, it means we don't know what this is. And I mean, I guess, you know, they're both hypothesized substances that fill up a lot of the universe. But other than that, they behave very differently. You know, dark matter we think is actual matter that doesn't interact with light, so it kind of makes sense to call it dark. Dark energy, which you might guess by the name energy, is not really, it's not matter, it's not stuff that sits on your table. It's really just called dark because we don't really know what it is. And this story might be apocryphal, but I've been told that this physicist in the late 90s, Michael Turner, he said we should call this dark energy because if we call it dark energy, the Department of Energy might fund our research. And the Department of Energy it pays all of my salary. So, you know. I'll say dark energy, it's a very similar murder mystery, except the weird thing with dark energy is that there is a super, super obvious murderer. It's obvious this person did it, but they have a stone cold alibi. And so we're left in this weird position where like, we're still pretty sure they did it, but it's like, how can we find a hole in the alibi? How is it possible this thing is still responsible? Because if they didn't do it, we don't really have good ideas for what it could be. I mean, you know, theorists, you know, this is their job. They write stuff down, and everyone else is like, okay, sure. But did what? The dark energy or the dark matter? Dark matter, I hope it's axions. Dark energy, we don't know. Well, okay, so the person we think did dark energy is vacuum energy. So quantum field theory. Hope I'm not getting too physicsy now, but it says that all space is filled with fluctuations, and that fluctuations has energy to it, and that's what we think should be the dark energy. But it turns out that if that were the dark energy, it'd be way, way too strong, like to the point that if that were the dark energy, the universe would expand so fast that like the atoms in your body right now would get like ripped apart. So like that can't be it because we all exist, right? So there's a lot of thinking of, can you make it weaker somehow? Or could it be something else? And if you came to my talk last year, I talked about how the dark energy spectroscopic instrument and the dark energy survey now have evidence of have evidence that it might not be the vacuum energy, it might be something different. The weird thing about it is the kind of evidence they find leaves people scratching their head. We're like what? Like what could do that? And so it's weird. Dark energy is weird. Yeah.
Dark matter is only from galaxies. So like, and also, if it wasn't dark matter, how would that affect time? Is there any speculation of how the dark matter affects our objective time, or any kind of general?
Yeah, so the first question is, are there places where there is dark matter but there aren't galaxies? And the answer is yes. So galaxies don't form everywhere that there's dark matter. It just forms in the densest part of the dark matter. To give you an analogy, it's kind of like snow doesn't fall randomly all over the Earth. It kind of falls on the mountaintops, right? So there's kind of this bias. We actually call this galaxy bias. So there's a lot of dark matter out there that doesn't have galaxies sitting inside of it, but we can still detect its presence because we can look at galaxies that are behind it, and the light from those galaxies, as it goes through that kind of galaxy-less dark matter, gets distorted by all the dark matter, and so we can map out the locations of the dark matter. That's called weak lensing, and that's actually one of the things that I work on. The second question was, does dark matter impact our experience of time? So if you could imagine the galaxy exists, it formed, we exist, even though there were no dark matter, the gravity that we would experience in the Milky Way galaxy would be less. And if you might know, if you watched Interstellar, that gravity affects time. So the answer is yes, but because the answer to the earlier question, right, that the gravity of the sun and Jupiter is way more important for what happens on the Earth than the dark matter is, then the answer is that it doesn't really impact any way that you'd be able to tell, that we can measure. What's important, though, is that if dark matter didn't exist, the evolution of the universe would be very different. So the age of the universe would be different. I'm trying to think if you had got rid of the dark, I'd say if you got rid of the dark matter, would it be older or younger? But that actually, it depends on what you do with that dark matter. Like, do you turn it, do you just disappear it, or do you turn it into something else? So it's kind of complicated. But the age of the universe would be different if there were no dark matter. Or I guess I should say, us making observations, the age that we'd infer, how old do we think the universe was before us, would be different. Yeah.
Detector you mentioned underground, it sounds a lot like a neutrino detector. So how does the smoke detector avoid neutrino interaction?
Yeah, so the question was, this detector underground for dark matter, looking for WIMPs, it sounds a lot like a neutrino detector. And that's because they are very, very similar. In both cases, you're looking for these particles that interact very rarely. So you go underground, you build very low noise detectors, and you wait for one of these interactions. But then he asked, how does it differ from a neutrino detector? Is that right? How does it avoid neutrinos? So to some extent it can't. That's what the neutrino floor is, right? But I guess maybe so the neutrinos would have different ways to interact with the material than the dark matter would. And so I wonder if maybe they can build detectors with different materials to try to preferentially select to make one stronger than the other, so that you see the dark matter instead of neutrinos, or vice versa. So for example, I know they like to build neutrino detectors with argon, but they built this dark matter detector with xenon. This is beyond my expertise because I'm not a particle detector. Maybe that choice is related to this preference for neutrinos versus dark matter. Yeah.
Yeah, so related to the last question, you said that black holes act as lenses and make light brighter. And you also said that dark matter affects the properties of light. So my question is, I thought that black holes absorb light. So the first question is, how do they act as lenses? And the
the second question is, if they affect the speed of light or properties of light, regular black holes like matter, and then how does that interact with the dark matter that is also affected by it, which then affects our perception of like looking at the telescopes to see all these things.
Yeah, so this question was about lensing, so about how black holes and dark matter, how they work with the light that we see. And one of the questions was, you know, he thought that black holes kind of gobble up all the light. And so, you know, how is it warping the light? Why does it not eat up the light? And that's because if you shoot a ray of light at the black hole, it's going to disappear in the black hole. You never see it. But if you have the black hole here and the ray of light's coming by it, you know, it doesn't hit the black hole. It just kind of curves around it. And so that curve is kind of the distortion that we see. But of course, behind the black hole, we can't see any light. Most black holes are so far away that behind the black hole is tiny, so you don't see that, but you can see the distortion. Although you might have seen the Event Horizon Telescope has a picture of the black hole. Another question was, does it affect the speed of light? And no, light always travels at the same speed in a vacuum. So light going through the universe is traveling at the same speed all the time. It just kind of changes its path, its trajectory. So it would have gone over there, but it turns it, and now it comes over here. So that's the effect has. And did I get all your sub questions?
I guess kind of my point was, if the light is going affected by both dark matter and light matter or regular matter,
Mhm.
is that just sort of the account for everything? Like that's sort of how we know dark matter is there?
Yeah, so it's kind of about, the question is about how does the bending of light from dark matter compared to regular matter kind of interact? And the answer is that, you know, we only see the total lensing from all of the light. And you can compare the amount of lensing you see with the amount of regular matter you can see. And you can see there's way more lensing. And so that's evidence for that dark matter. And so when we model, you know, like for example, we look at a galaxy cluster, it lends stuff behind it. When we model that lensing, we have to take into account the stuff that we can see, and then we assume the stuff we can't see is all the dark matter. And so we kind of map out where that is in relation to the regular matter. Yeah, and everything is lensed because dark matter fills the whole universe. So all the time we're looking out at the universe, kind of like looking through a funhouse mirror. Everything is kind of slightly warped. And so our job is to kind of undo the warping and figure out, you know, what does that look like, and what is the stuff that warped in between, because that lets us map out this big cosmic web of dark matter that surrounds us. I think that's it. Thank you very much.
Let's give him another round of applause. Okay. I need the clicker.